easy. And I will hand out electronically on the 14th December, because I know you have many examinations and it will help you a little bit. And well, that's a fantastic number.
So we don't have to end it. It could also be the end of the world that day. So we don't have to end it. Make it 20.
I see, are you saying these cancels? Sometimes it's reflection. Okay, today's theme is a continuation, but let me write it. With emphasis on Hamiltonian mechanics. So, I will recall a good deal from the last lecture, so I'll recall some of the definitions. So, symplectic manifold is a pair. The two conditions are satisfied. They look harmless, but they're not. So the form is closed. Omega equal to 2 form. So closed 2 form. And omega is non-degenerate. Of course, you know what that means, but let me just remind you that there are several ways to think about it. So, one way to think about it is that all the vectors that are perpendicular to, so for all points in the manifold, the 2 form is the 2 form of the manifold. The tangent vectors which are perpendicular to the tangent space is just 0. So there are no tangent vectors which are perpendicular to the full space. So these are the set of vectors V in the tangent space such that omega V is 0. This is 0 as a form. And another way of saying that, and I think maybe it's even better, is that it's equivalent to saying that omega defines an isomorphism between the cotangent bundle and the tangent bundle. And the isomorphism is you take a tangent vector at a point P and you map it to the cotangent, well, let's say omega at P, cotangent vector. An isomorphism. So a non-degenerate 2 form which is closed. It sounds harmless, but is actually a very big condition. So we have seen that our first example was we looked at the direct sum of a vector space and its dual equipped with a standard form. Equipped with a standard form, and which I wrote down as minus d lambda. lambda is the Liouville form. And in coordinates, we computed it. So how do you compute coordinates? That means you take a basis of V. And this means that a vector is expressed as a linear combination. Here are the coordinates of V. And those are the coordinates. So we quite often just write Q is the coordinate of V. And then there's this funny thing that a covector then in V star we write as some, let me be consistent, P1 of P, dQ1, that's a one form, Pn of P, with the coordinates of P here, dQ. So that's sort of the canonical way to write a point is differential form on the dual space. And so Q of P, the coordinate of P, is we always just write for P1, P now. And then we say that PQ are called canonical coordinates. I mean, of course, they depend on the coordinates Q, but otherwise not. So. Associated to the coordinates Q. And here and then in these coordinates lambda, we calculated out what lambda was. I will shorthand notation all the time now. So that means this. We computed that out. And omega, correct sign, is dQ. P, and that's just of course dQ to P. And these are the physics letters that you will see in any discussion of classical mechanics. I'm sorry, my didactics is not very good. Okay, now you recall the canonical alternating form alternating bilinear form on V plus V star. This alternating form is the same thing, that's what I want to say. So remember, I wrote it many times, but I'll write it again. So it's the canonical alternating bilinear form. And this is a linear 2 form. So this, as interpreted as a differential form, let me emphasize what I'm talking about in this manifold N, which is the direct sum here of those two things, is exactly omega, the standard form. So I'm calling this omega standard. I hope you understand. A priori, this is just a bilinear form. But this interpretation means each tangent space here is identified with the vector space. And so at that tangent space, you just evaluate this alternating form. So it's just a constant alternating form. Interpreted as same thing. And let's compute it in coordinates, the basis. So, I'm sorry, I'm getting confused here with my didactics so that you can see. So, oh boy. So, this would be another notation which is effectively the same, so I'm calling something a symplectic vector space. So again, here I'm talking about everything as a manifold. Here I have just a bilinear form. This means this is an alternating two form, which is of course, what am I writing here? So, an alternating two form, which is non-degenerate. Of course, it's automatically closed because it's constant. Right? It's just a constant form. Is that clear? It doesn't change from place to place, so d of it is just absolutely constant. Fine. So closed is automatic. So this is an example of a symplectic manifold, but it's a symplectic vector space, so it's a vector space together with a real vector space, or in this context, real vector space could be complex, but not real. Okay, so this gives us a little bit of discussion of symplectic linear algebra. As one of the main examples of the subject. Just in other words, forget the symplectic. It is a symplectic manifold, but let's just do linear algebra. Symplectic linear algebra. So let W omega be a symplectic vector space. And let's let U be a subspace. Now what I mean by that, I mean really just some linear subspace, an R linear subspace. So when you do linear algebra, the first thing you do is look at the vector space and additional structure. In this case, a symplectic form, an alternating bilinear form. And the next thing you do is look at subspace. Obviously, this is the next thing you do. So the thing you do before doing anything else is you look at the pullback, if you wish. So we have this U into W, call it iota, and then we look at the pullback of the form. Let's call this iota U. Iota U is a lot of notation, but I'll stop with this notation. This is an alternating bilinear form on U. All right? You can think of it as a restriction if you wish, but you're pulling it back to the subspace. And you ask, what about degeneracy? So the first question you ask is, what about...
Professor, here the push forward is just, when you define the pullback, you use the push forward. And here, the push forward is the same as map, no?
Yeah, that's right, because it's linear, that's right. Right. And I know I'm being a little bit pedantic here, I'm being a bit pedantic, but what you're really doing here...
Is you restrict the form.
Yes, let me just, I'm just restricting the form, but that just means, so U pull back omega of U1, of UV
It's just 2D.
It's just the same thing, right? That's what you're saying, Michael. So U, I, and U is just omega U1, U2. Okay. So if you like, let's call this just the restriction, but same thing. The question is, what about the non-degenerate, the degeneracy? Of this pullback form. Okay, I'll call it omega restricted U. Well, it can be everything. So let me make a sequence of remarks, really silly remarks, but that's the easiest way to learn. So remark is if U is odd dimensional, Sorry.
I think it's degenerate.
Then it is degenerate.
It should be.
Because if it's odd dimensional, then this thing is degenerate. And the reason is symplectic vector spaces are even dimensional, right? You see, if you don't believe me, just look here. So then in fact, the degeneracy, which is what I mean by this vector space here that I wrote here, this as the degeneracy of the form, then the degeneracy of this form is positive dimensional, for sure. So there are a number of words that we associate, various descriptions of various notations for degeneracy. For various types of degeneracy. Some being very important in physics and actually being introduced, the role of these spaces being introduced by people like Dirac. The first thing is U could be called isotropic. That means what you think. It means the perpendicular space to U, this is my notation, so let's just try to get used to it. Everything that's perpendicular to U contains U. Now, this is getting a little bit crazy. The orthogonal complement of something contains it. But it's very possible, right? I mean, because you have vectors here which have where the thing is trivial. So this is called isotropic. We'll have more experience, so just believe me. If you don't believe me for a minute. It's very easy. We'll have many examples in a minute. Okay? So, a stupid example for this. But maybe not so stupid. Is if it's one-dimensional, then the form, right? The form restricted to it is degenerate. So its orthogonal complement contains it. Another possibility is that's the other way around. U is symplectic itself. So that means that the orthogonal complement of U intersect U is nothing, so it's just the opposite. It means that omega is not restricted to U, is really a symplectic form. A third thing which is important is U is coisotropic. This is related to homework exercise. And this is, well, it means that the orthogonal complement of U is contained in U. That's really weird. The orthogonal complement of something is contained in it. And the last one, which is very important for many considerations, is U Lagrangian. So U Lagrangian, let's go on down here. U Lagrangian. These are special, very important things. This means that is both isotropic and coisotropic. And coisotropic. This means that the orthogonal complement to U is U. Okay, those are the four kinds of subspaces of a symplectic vector space. In particular, Lagrangian will play a big role in many considerations, and I'll talk about it in the next lecture. Well, let's do some examples. Let's go back to the old example, W equals, so examples. W equals V plus V star, equipped with the standard form. So this is the symplectic vector space. And then you see V and V star are Lagrangian. Let's just check that to convince ourselves of that. So why is that the case? So let's say omega standard restricted to V. Well, you can only apply to vectors V, so that the functional part here is 0, and functional part here is 0. So this functional part applied to that, which is 0, minus this functional part. Oh, here should be prime. So applied to this thing. Well, let's see. So it's, and the same thing for V star. And of course, the dimension of these things. So what we check is, the way I like to check it is that the space is isotropic, but half dimensional. It's the same thing. It's the same thing, because keep in mind that to check any of these things, a key fact is a stupid fact that the dimension of any orthogonal complement is just simply the codimension. So it's the dimension of W minus the dimension of U. So you can, this really helps. You see, if this thing is bigger than half dimensional, then its orthogonal complement is smaller, and therefore it cannot equal itself. So that's basically what you have to check here. So these things are Lagrangian, always, and it's a fundamental example.
Is it true for all U, for which is a subspace of W?
Yes, because W is non-degenerate.
I mean, is this true for all the W and U? I don't think it's true.
Let W be a real vector space, for example, or a complex vector space, or any kind of vector space, equipped with a non-degenerate bilinear form. Right? I formulated it here, of course, in this context, but I mean, that's the meaning of your question, right? Of course, it's just you write down how many equations you have, right? So, you understand what I mean by how many equations you have? Just independent equations. Okay, so this is a key fact in computing these things. In the homework, I asked you to show it's not difficult. Codimension U equals 1 implies U is actually coisotropic. This is for silly reasons. But it's a very important case. Just a check. Let me see, Lagrangian, coisotropic, what other words do I have? It's symplectic. So I should give you some example. I hope, let's take V plus V, let's take this example again. W. Let's try something here. Let's try U, you see here, this is Lagrangian, that's V star. And here, this is V, that's Lagrangian. And now let's try U diagonal. Well, it depends what that is. I'm not sure what's going to happen here. So let's take, U will be someplace in here. Let's try to find something symplectic. Half dimension, not necessarily we're going to find it, because it might even be odd. So something diagonal in there. Let's try this. For example, let's just try to take a basis, E1 through En, basis here. I'll just try something. F1, Fn, dual basis. Let's try something like the span of E1, well, something completely stupid. F1, E3, no, what, E1, F1, and now the rest of them. So, I don't know, E2 through En. Let's try that. Okay. Now, what about this space here? Let's call that U1, span of the space in here. Is it clear to you all that this space is symplectic subspace? This is symplectic. Because it's just the restricted form, is just the standard form here. And now the orthogonal complement of this thing, well, is what's orthogonal to that is, well, everything. So it's the span of E1, E2 through En. So that's completely clear. And now all sorts of crazy things could happen.
So the orthogonal in the span above, or is not the orthogonal in the whole space?
I'm looking at the that's orthogonal. Thank you very much. So I forgot the rest of the space, right? So that's the span in here. No, I need to, yeah. Thank you very much. So let's write, this is our span, yeah, it's orthogonal complement in U1. That's what you're saying, right? So, thank you.
Not in U1.
So, let's just say the orthogonal complement U1.
In U, not in U1. If you define the span, like...
Oh, in U, yes. This is U. Yeah, this is what I want. I just wanted to get experience of computing orthogonal complements. What's it going to be? I guess it's going to be
F2.
It's everything with 2 in it, right?
No, it's F2 to Fn.
Yeah?
That's U1 orthogonal, not U. That's U1 orthogonal, not U orthogonal.
Well, maybe we're talking about 2 different things. So I'm talking, this is U. What is orthogonal to U in W? Oh! These are certainly not.
That's what I'm saying. No, the F's are and the
No.
E's are not.
This is correct now.
Is correct?
Yeah, E is orthogonal to E.
Okay, the too many things that we're talking about. I'm sorry. What I'm talking about here is this, right? That's what you were saying. I forgot the 1, right? Yeah. So, this is what I wanted to say with this example. You see, this thing has a huge orthogonal complement, but it itself is symplectic. And you have a big conjecture here, of course. If you have a symplectic subspace, the orthogonal complement is symplectic, right? So if you have a bilinear, it's the same thing with bilinear. Your remark about bilinear forms has nothing to do with symplectic. You have a subspace where it's non-degenerate and take the orthogonal complement. The key is it's complementary, and the restriction is also non-degenerate. So you go through all these examples and work up some intuition.
But since, I wanted to ask you, so since you have a form on it, a bilinear form, you can always talk about an orthonormal basis, no?
That's right.
Okay, so since it's...
What do you mean by orthonormal basis? So let me just hear what you mean.
Orthonormal basis is a basis in which every two orthogonal vectors are, every two vectors that are different in the basis are orthogonal, and the absolute value, the length, is 1. E1, E1 is 1.
What, E1, E1 is 1?
E2, E2 is 1, and so on. You can always have it? No.
What is E1, E1 here?
No. No, it's 0.
Yeah, it's good you asked this question. It's exactly the point. Yeah?
So you don't have any orthonormal basis.
Yes, you do, and I'd like to talk about that. But you have to think of it just slightly differently, but along the lines you would like to think of it. So it's the first question asked. Do you have an orthonormal basis? And we saw this is a good question, but that's only the first question. The second question.
That somehow means that the symplectic form, could it define a norm on that space?
Say it again, please.
Could the symplectic form, I mean, for example, the omega standard, could it define a norm on the space?
No.
So because usually the bilinear form
It's not
can-
positive definite.
It's not symmetric.
I like very much your questions. We should try to find some way to define a norm, right? But without additional information, we cannot. Okay?
That's why we cannot say that the orthonormal basis is the usual thing.
These questions are so good, let me make a small diversion. Which was almost the first lecture I gave. So this is a little diversion to try to answer the kind of things you're... So, example. I think I should have given the example. Let W be a complex vector space. And let H be a Hermitian structure. On W. Now here I mean not necessarily positive definite, I mean just non-degenerate. Then, of course, you separate H into the real part. Actually, the good sign here to take is probably minus I times the imaginary part. Sorry. And the letter omega is, in this lecture, very appropriate. So,
What is a Hermitian structure?
huh?
What do you mean by a Hermitian structure?
So, it's, depending on your choice, it's real bilinear. So depending on your choice, it's complex bilinear, linear in one argument and antilinear in the other. And if you reverse the arguments, complex conjugation comes outside, and it's non-degenerate.
So it's also a bilinear form.
Real bilinear, but this is a complex vector space. Okay, so it only respects the complex structure with, as I just said. Okay? Yeah? And you check that this implies that omega is a symplectic structure on space. Now, you could go in reverse. If you don't need to be very clever, just say, well, symplectic vector space is even dimensional. So if I'm a little bit clever, I will introduce a complex vector space structure on that, so that if I do it in the right way, this omega will be the imaginary part of a Hermitian structure, and the answer is you can do it. Okay? And so this is what you're driving at, somehow getting a norm or something. I mean, because the Hermitian structure, well, if it's positive definite, then you really have a norm, otherwise. Okay. But it makes sense to talk about the norm in Hermitian geometry. And in fact, the real structure so G is the real bilinear form, is symmetric. Is symmetric, of course. And the way you get omega, now I'm going to perhaps make a mistake. It depends on something here. Yeah. So the real and imaginary parts are related by something like this. Okay, and maybe I put the I in the wrong place. It could be in the first. So you're either dealing with a non-degenerate real structure here, and then you define omega like this, or otherwise. So this should be, I should be in the sum of this. So that partially answers your question. You look for a norm, and you look for a real structure, and you find it like this. So let's look at a good basis. So a good basis. So this is what you're all talking about, like an orthonormal basis or something like this. So a good basis. Well, would be something like this. You just take e.g. for d plus d star equals w, and omega equals omega standard. Let's take a look here. You know what to do. So we have the basis. I'll just repeat myself terribly, I apologize. The basis and the dual basis. So dual basis, basis. So B star. And now, what is the matrix of the form, the canonical form? I don't know if you've ever looked at this or not. Let's look at it. Let me draw it as a big matrix. The way you find the matrix of a bilinear form is it's just the pairings. And the order of these two n vectors should be like this. Or at least this is one good order. And now it'll clearly be in block form. So the e's paired with the e's. Remember what this thing is. I don't know, if you don't mind, I will just write all these terrible things that you need to compute here. Let me write examples. EI with EJ, that's 0, right? EI with FJ, I hope that's delta IJ. All right? So EI first and F second lands here. And so this is the identity. And now F, so the row goes first. So Fi first and then EI, it's the other way around here. So this is minus the identity. And this is the way it is, right? So just compute it. It's a very good basis, right, for that thing. So if you let X and Y be coordinates, or I don't care, P and Q, why not? So Q and P associated coordinates. Then A of QP, well, A of So this is, let me write this as some big coordinate x. So A of x, y is then x transpose with this matrix. So this matrix we call J. J. Right. That's how you do the matrix of a bilinear form. In coordinates x, well, I like to use P and Q. So that's phase. Still doing symplectic linear algebra just as a good example. J seems very important. So that was for this example, and the key remark is if W of omega is a symplectic vector space, then there exists a basis of W so that A omega equals A. Now, in that sense. So what that means is the correct, this is a little bit vague, so the i.e. the correct interpretation of the statement is there exists a Lagrangian subspace, there exists Lagrangian subspaces there exists Lagrangian subspaces. Don't forget these subspaces are Lagrangian. There exist Lagrangian subspaces L1 and L2 so that W is the direct sum of Lagrangian subspace. So this is the correct viewpoint that you can all you see these are WV plus V star. These are both Lagrangian. If you just identify V with V star, I mean the second space with V star. But in fact, in this way you can define. In this way, L2 is naturally defined isomorphic via omega to L1 dual. If you don't believe me, I'm going to give you a map from L2 to L1 dual just by taking a vector here, I don't care, V, and go to omega V dot. Okay. Now, why is this an isomorphism? It's because this cannot be 0 on L1, right? Because if it's 0 on L1, that means the orthogonal complement to L1 is bigger than L1. Do you see? This is outside L1. If you have something outside L1 which kills L1, this cannot be 0 on L1. So this is definitely not 0 on L1. If it were 0 on L1, that would mean that L1 plus this one-dimensional subspace would still be isotropic. And Lagrangian means isotropic and maximal dimensional. So it's definitely not, that's definitely not the point. So in fact then, a Lagrangian direct sum is above W equals W1 like this is the same thing as just L1 plus L1 star, or let's just write it without indices, L plus L star. So there are many ways, and now you can write down the symplectic basis. So now write down A as above. And the A of x, y, if you take bases of this and the dual basis, it's just x transpose J. So the key thing here is in the subject is Lagrangian decompositions. And from the point of view of quantum mechanics, Lagrangian subspaces are very important. In fact, I think Dirac, in his first paper, if you look at Dirac's first paper, he really has the word Lagrangian all over the place, doing in some sense, symplectic geometry. So let's look at a simple example. So the simplest example is two-dimensional. So the dimension of W is 2. Okay. And J is your favorite J. The physics J is this J, and the complex analysis J is minus this J. So it's a confusing point. Okay. So this is J on R2. Now, the symplectic group in this case, so SP2, so in general SP2n, which I will discuss in a minute, but just SP2, these are the matrices, these are the operators, A, that are isometries of this structure. So A transpose J, A equals J.
Professor, could you use another notation? Because I think the A will confuse you.
Oh, yeah, let's just B, okay? Yeah, I use A all the time. My first name starts with that. You know, Banach named his spaces were all B. And Hilbert's spaces were all H. B. Okay, so these are 2x2 matrices. I didn't say it explicitly, but it's obvious because I have this 2J here. So let's have some fun computing what's going on here. So let's see here. B, let's say B is ABCD. This is a little bit nonlinear, but here it's not so bad. So what do? It's A, C, AC, B, D. Now watch out, you guys are really much better than I am in calculations here. So J is 0 minus 1, 1, 0 times the same matrix now, but just B, A, D, B, C is supposed to equal to J. 0, 1, minus 1. Okay, that's a quadratic equation. So let's compute it out. That's the same. Let's compute it out very slowly. Let's multiply the left one out. So it's C, D minus A minus B equals the same thing. So C, D minus A minus B. And this is equal to AC, CA with a minus sign, AD minus BC, ha ha ha, AD minus BC, BC minus AD, and this of course is 0. So if you multiply this out, you see immediately that in 2 by 2 case, symplectic is really dumb. It's determinant 1. So this says the symplectic group, so you see that this says this determinant is 1, so it says that SP2R is equal to SL2R. Now that's very, very rare, but I just wanted to emphasize this little point. And this gives rise to a discussion of what is an invariant of a Hamiltonian system. So keep this in mind. And now let us go to Hamiltonian systems, but even this is a 2 by 2 case, because I mean, you know, why not? I mean, let's have some fun. And everybody, nobody's threatened by 2 by 2 matrices, right? Even I'm not threatened. So let's have some fun. We can have now 15 minutes of fun. Okay. So 2 by 2 fun. And let's see. Oh, that's Freudian. Okay, I'll change that. Maybe I should have gone to 3 by 3, but I think that's I think I'll stay at 2 by 2. Maybe 1 by 1 is more like real life. So let's see what happens. So the homework. This is a beautiful homework problem. You can have fun, but it's completely easy. Just do some calculations, have fun. We look at quadratic Hamiltonians. In fact, the homework was formulated in general, but let me just formulate it here in the 2 by 2 case. So a quadratic form in 2 variables. Yeah. So this is a symmetric matrix. Quadratic form is a real quadratic form, quadratic Hamiltonian in 2 variables. A symmetric matrix. So what does that mean? A is anything in this case. B is anything. So, and this is B. A, B, C, D. D is anything. All right. But it has to be symmetric. So these two have to be the same. But here there's no condition. And then that means the Hamiltonian is a quadratic form. So it's QP times AB, B, D, QP. See, we can have fun with 2 by 2. It's not difficult. And now we have some interesting thing. Now we have the Hamiltonian vector field. That's the homework exercise. You start with this and you get the Hamiltonian vector field. Remember, you compute it in the following way: d of h. So you just take this quadratic form, take d of it, and it has to be the contraction with xh of the standard symplectic form, and that was the exercise. And I may be wrong about sign someplace in this exercise, but I think that, well, x for sure is a linear field, because you take d of a quadratic, you have something linear. And linear fields are the form, so So the ODE, for example, is of the form x dot equals mx. So x is here, qp.
I got minus AB minus BD.
Yeah, you got it in your head already.
No, I got it in my homework.
Okay, what did you say? So I would have said that it would have been b minus b, okay, a here or here?
No, when did you change the order of the variables?
I don't know, a, d. Maybe.
And
Either that, I'm not sure, I can't remember, I'll do it if you wish, but it's that, right? But the main point is this is an arbitrary matrix of trace 0. Okay, this is an arbitrary matrix of trace 0. So trace of this matrix, this is M. And trace of this matrix is 0. So that's that, that's the ODE, and now the integral curves. We know what they are. They're x of t equals e to the mt. And I hope we learned a little bit from my lectures how to say, well, if you have this one parameter group, you know what, that's what you're looking for. You're looking for the solution to this dynamical system. You have some base point v, and you're looking for this orbit. You want to understand this orbit. So you say, let's look for, if this is an eigenvector, you're in big business. So you want to look for eigenvectors of M. And that means you want to try to diagonalize M. You know M is not necessarily diagonalizable, right? Now, what does it mean to diagonalize here? It means to preserve the structure at hand. If you try, if you're dealing with symplectic, well, here it's very simple because it's just a matrix of determinant 1. It's particularly simple, but in general it will not be so simple. So, i.e., this means, in general, conjugate M by, now you guys give me, what letter am I allowed to use here? Oh, B, right? You conjugate by a symplectic isomorphism, because that's the whole thing is symplectic. And B is, in this case, symplectic is stupid, but it's still interesting to do. So, in this case, let me just say in general, B should be in SP2NR, and that's simply the same equation, except much more complicated. And so the question is, given a matrix of some form like this, of some special matrix, like in this case, well, in your homework you did it. It was B minus B transpose, A a symmetric matrix, and D a symmetric matrix. Given something like this, try to diagonalize it. That's the goal. Now, a new phenomena occurs, and you already see it in dimension 2. So, again, everybody's used to diagonalizing Hermitian, symmetric, and all this kind of stuff. Unitary operators are diagonalizable, all sorts of blah blah. Of course, there's always some exceptions. We know what they are. But most operators are diagonalizable. Here, that's the case too, but completely new phenomena, and you see it even in dimension 2. And this is one of the most beautiful examples of something in the simple case that reflects something non-trivial. So let's try to diagonalize in dimension 2, and then that will be the end of our fun. That's great, we have 9 minutes more of fun. So, okay, here we go. So let me repeat, the goal is understand, you see, if you just say diagonalize all this technical stuff, that's not very interesting. Just try to understand the action of SP2R, okay, it's just on this set of matrices. So set of M such that trace of M is 0. The condition here is very simple. So that's a vector space. That's a vector space. You have one matrix, you add it to another, it's still trace 0, and you multiply and so on. That's a vector space. So this is a three-dimensional vector space. And we have seen, I hope that you've gotten from my first lecture, is the first thing you should do is look for invariance. So look for an invariant of this action, of this conjugation action. What is an invariant of this action? So look for an invariant of this action. Invariants, but there may be many. And the best thing to find is a quadratic form. Is it? Or a bilinear form. So, in other words, an invariant geometry. So, the question is, on this space here, what is the invariant geometry? And all of us have had a lot of experience in mathematics and so on. The invariant bilinear form is wonderful, so let's call it B. No, small b. B, let's call this space, where'd it go? Space. Oh, this space here, trace 0. People call this German SL2R. Let's call it that. So I'm looking for a bilinear form on these trace 0 matrices, SL2R cross SL2R. For those of you who know about Lie algebras, this is just the Lie algebra here. So a bilinear form. And here's a good one. B of C eta is just, and I'll take the physics norm of this trace C eta. I've told you in the first of the class, every bilinear form for conjugation comes somehow from trace of something, right? Somehow comes from trace. This is the simplest thing. You might think the determinant should play a role. Well, it's somehow related to that. Let's see here. The norm, the quadratic form, let's call it big Q because there are too many Q's. The quadratic form associated to this, the norm associated to this, say norm of this thing is 1/2 trace C squared. Right, I mean, you have the bilinear form, the associated norm is just, let both things be the same. Now, that's what you asked for. You asked for an orthonormal basis, right? You would like to see an orthonormal basis. Every physicist knows immediately an orthonormal basis.
That thing is just a determinant.
Hmm?
If you compute that thing.
You compute it in your head, it's the determinant. Yeah, it's plus minus the determinant, right? I mean, you know that. So this is plus minus the determinant, but that's a horrible looking thing there. Yeah, it is. Yeah, I guess. Let's just do it out.
No, it's not determinant.
Well, what is it? Minus the determinant?
No, it's the determinant.
It is with the 1/2 maybe. Is this?
No, it's minus the determinant.
Yeah. So I think this is minus the determinant of C over 2.
No, without the over 2.
Huh?
You have So you have minus determinant of the
Oh,
first.
yeah, yeah, good, so the 2 is gone. Yeah, that's that's the good reason, yeah, sure, the 2 is gone. So that's what that thing is, but that's horrible, it's minus a squared, minus b squared minus ad. So,
B squared plus 8.
huh?
With the minus is B squared.
Yeah, so I don't understand that quadratic form, so I'm gonna look for an orthonormal basis, right? I mean, let's look for an orthonormal basis. And we have a lot of experience. So I'm gonna write down what I claim is an orthonormal basis. I've just had a lot of experience. I know that this is a good thing. By the way, you can check easily this has norm 1. I know that this is a good thing. These are closely related to matrices you see every day in physics. And I know this is a good thing. You would find these things independently just by experimentation.
Those are the Pauling matrices.
Yeah, very close to the Pauling matrices. So this, if you check it, this is an orthonormal basis. Okay. And now I want to draw a beautiful big picture here, so let me draw it on one blackboard here. So this is an invariant. So that means the level surfaces of this norm in this orthonormal basis. I will now use the orthonormal basis. Any guesses what the signature is of this norm?
But this is, so that is a real vector space, not a complex vector.
It's real.
It's a real vector
Yeah.
space.
So this is really a real bilinear form. This is everything real. Let me write it in coordinates. In the coordinates here, x of a matrix equals x1 e1 plus x2 e2 plus x3 e3. Suddenly it's getting confusing. So the quadratic form is x1 squared. This is the perfect thing. So this is the Lorentz form, signature 2-1.
Where is it minus?
Check it. That is, well, let's check it. So it traces minus 2 divided by 2. So this is a metric of signature 2-1. Here it is. It's real life. You know, when I was a kid, or your age, I couldn't believe anybody was studying things that are not positive definite. I was too naive. I mean, look, you haven't done anything here, you have this. So let's write a picture of this thing. So these are the usual 3 axes. Maybe just for fun, I'll put here a matrix here. This is the E3 axis, so this is the matrix J. And the matrix E2 would have been here. This is the matrix 0, 1, 1, 0. This has norm 1. This has norm minus 1. And here we have the matrix, what do we have here? 1, minus 1. And now you have the light cone. Maybe I'll use some more colored chalk. So maybe a little bit of color here. So the light cone is where that norm is 0. This is a light cone where this norm is 0. So let me emphasize that here. The cone is x1 squared plus x2 squared minus x3 squared equals 0. These are negative vectors inside the light cone and positive vectors outside the light cone. Now I'm sorry, I'm very dogmatic about this. The problem was to diagonalize a bloody matrix. Right? Sounds stupid calculation. I changed the whole setting by saying, I'm going to try to understand this action. Okay? To try to understand the action, I said, let's look for an invariant. To look for an invariance, I told you to remember the first thing in linear algebra, that bilinear forms are invariant. And you're going to find trace forms that are invariant. It's about the only thing you have. So I write down the only trace form, and I find a Lorentz geometry in this set. And then I get really, really, really excited. Yes? And so I draw the orbits here. I figure out what the orbits are. Now you can figure out and have fun yourself. I can't do it. You probably are better at computing. Maybe this is a dish. I can't do this. Can you? I have to do it physically. See this cone? Here's this cone. Here's a dish going like that. That's a two-dimensional dish. You see it? Going asymptotically out to infinity. You can write down. I mean, it's a level surface of this thing. It's a level surface of this thing. So you know what it is. It's a surface of, right? It's a surface of, well, it's obvious. It's a parabola rotated around you. I just can't draw it. Okay? This is a dish down here. And the interesting thing is, this is also a surface of revolution, some obvious way, but it's a hyperbola.
Professor, may I ask a stupid
Sure.
question? You said orbit. What is the action to?
Oh, I'm sorry, yes. So, I'm sorry, yes. I didn't say. So, an orbit here. An orbit, say, of some point. Let me dramatize it. Say, an orbit of a point somewhere here. Okay, here. So, an orbit of C is, if the group is G, I write it GC. And this is everything you can get, B, C, B inverse for B in SP2. It's everything you can get by applying the group. Okay? Okay? So I purposely put this one example out here. That orbit, you see this is an invariant. And so the orbit has to be contained in the level surface of this invariant, because this invariant doesn't change. And you, in fact, can check it is exactly the level surface of it, and it's exactly something like this. Okay, so it's this is on the outside of the light cone, it's a hyperboloid of revolution, and on the inside of the light cone, it's a paraboloid of revolution, or I think you call it, right? Two totally different phenomena. Totally different phenomena. Now, you take this guy out here, and you say, can I diagonalize it? Yeah? And I say, yeah, because this hyperboloid, you just look at the orbit, you come over here, here's the diagonal. Okay? So the diagonal for that guy, so this guy here, let's call this C plus because we're in the positive light cone. So C plus is conjugate to some number, lambda, times whatever this thing is.
Where does it intersect those things? Where does it intersect? Why does it intersect the light cone?
Why did it?
Not light cone.
Just check it. Just check, I mean, it's a level surface of this, and so that means the other two coordinates equal to 0. So, well, you can check. Okay?
The axis, not the
No, it doesn't intersect with light cone.
No, it's not intersecting the light cone.
But you made it intersect.
No, that's not
That's
light
weird.
cone.
Oh, that's wrong.
It intersects, so what is this axis? This,
This is just the axis of.
have I screwed up the axes?
No. C1.
So, it depends on what the axis I have taken, right? So for sure, yeah, no, it's completely, yeah. So that axis, no, it's completely correct what I said. That axis is x2 equals 0, y, x3 equals 0, right? That's that axis. Okay? So for every value of this quadratic form which is positive, it hits that axis. and I'm in a value which is positive. You see what I'm saying? So it hits that axis. That axis, it actually will, I think, will hit it in 2 points, right? Because plus minus. So I have some choice of the point. Okay. But you see, therefore, I diagonalize it. So everything on the outside is diagonalizable. Yeah? And now let's take something on the inside, say in here. See, but I'm emphasizing minus. So let's look at the orbit of C minus. Well, of course, it could be either here or here, but in each case, it's the same thing. This will be, both of these things equal to 0, so that will be, my freedom will be in minus x3 squared, and so I can always solve the problem minus x3 squared equals something, and it will intersect here, here. So this thing will be equal to lambda, maybe plus minus lambda, it doesn't matter, lambda times j. So I emphasize the eigenvalues here are real, and of course anybody can compute the characteristic polynomial of this thing. What is this thing? It's lambda. It's the characteristic polynomial would be, say, z minus lambda, determinant.
Minus 1, 1.
So it's z squared plus lambda squared. So it's plus, this means the spectrum here of this thing minus is plus minus I times lambda. Right? So two completely different phenomena depending where you are originally. So the ODEs, when you linearize the, when you find the eigenvectors and eigenvalues of ODE, you can find them. They are, except for these things in the light cone, you can find them, but totally different phenomena. Yeah? Totally different phenomena. Okay? So the dynamics of these two things will be completely different. You just write it down. Okay? We've had too much fun and we're going over. Let's see if there's anybody outside. Nobody's outside. Everybody quits. The semester's finished for the rest of these people. Let's just have fun. E to the, what did I say, diagonalize? Well, I can diagonalize lambda j times t. This is j. Right? Well, I mean, I can put this lambda in here just for fun and make it just e to the jt, more or less e to the jt. That's all that counts. So e to the jt. And now let's write this down. This is identity. I'm writing the power series down for this thing.
Cosine jt.
Do you know what else by heart?
Isn't it cosine jt plus sine jt?
Yeah. Well, if you're, it is cosine p, right? Times the identity plus sine t times j. Right? So these are the waves, these kind of waves. Right? This is very interesting. That's the phenomena inside the light cone. Yeah. That's inside, this is for C minus. And now outside is, let's use this matrix here. So e to the t, is anybody better than I am at this matrix? This should be very easy, right?
And the square is I.
E to the power.
The square is I.
Huh? Somebody knows by heart?
The square is I. The square of the matrix is I.
Yeah, the square of the matrix is really the identity here. So it's always with plus sign. So it's hyperbolic cosine t. Totally different phenomena. Hyperbolic sine, hyperbolic cosine, times the identity. Oh, this matrix we should call something. I don't know. I don't know, H. Plus, and I think if you look at it, it's hyperbolic sine t times H. Okay. I could have made some sign mistakes here, but
So you just said us that the orbits look like that. Like you have to compute them somehow.
absolutely. So
Because I mean you said us like the orbits look like that, but we don't know.
well, I thank you for pointing this out. No, you have to work. The one thing that is completely obvious is these orbits are inside the level surfaces of this invariant.
Yeah.
The second thing is if you check, it's easy to see that the orbits are two-dimensional and the level surface is two-dimensional. So basically they're agreeing. But what you need to really then check is that the orbits are close. And then you have to work a little bit, at least I do. So it's an interesting, maybe I'll make this as an exercise. But it's a beautiful exercise to really check that this picture is right. And on the light cone, of course, the matrices on the light cone here, the matrix here that you get that's not diagonalizable is this one. And the matrix down here that you get is this one. So it's a very, very beautiful picture. These are the non-diagonalizable ones in the cone. These are the diagonalized ones, and they are diagonalizable to two different kinds of diagonal matrices with two totally different kinds of phenomena. I mean, you know hyperbolic functions are completely different from... I hope I've gotten this right with the signs.